we will now be talking about the effective net area. Okay, so again, from what we have discussed earlier, net area is the area of the cross section of the tension member considering the holes. Okay, so now we will be, so one important step in analyzing and designing tension members is the determination of the effective area, which considers two two factors. First, the presence of the bolt holes. So this one is pretty obvious, right? So if you have a bolt hole, meaning the cross section is diminished, and what we call the mechanism of shear lag. So we will be discussing a bit about this later on. Okay. So for our purposes, for design purposes, so usually we are given the bolt diameter, right? However, we do not use the nominal bolt diameter. Okay. So in our case, we use the so-called effective bolt diameter. Very sorry. So I think this is not responding. Okay. So let's wait for a while. At saka naman, hello, hello. Uh, Hello, do you hear me? Narinig ako. I guess this one is okay. So, okay na? Do you hear me now? All right. So, apologies for the technical glitch na. So, okay. So, let me continue my discussion. So, doon na tayo sa bolt diameter, right? So, usually we are given the size of the bolt, right? However, for design, we will be we will not be using the actual size of the bolt. So in actual, we are when we are putting holes on steel members, we do not fit the hole such that it is the size of the bolt. So usually we put some allowance on it. Okay. So for installation, for bolt installations, the size of the hole must be uh, the bolt diameter plus 1/16 inch. Okay. However, due to some construction issues or workmanship, no, so that hole may be a bit oversized. Okay, so we also, so in analysis and design, we also consider oversize of the holes. So for the calculation of effective area, we use what we call the effective bolt diameter, which is just equal to the nominal bolt diameter. So this is the actual size of the bolt. Okay, so plus 1/8 inch. Okay, so if you want this in SI, you just have to convert this to SI. Okay, so it would be about around let me see, around 3.175 mm. So you add that to the bolt size. Okay. So now, how do we actually determine the net area of a tension member? So we determine it like this. So the net area is just the gross area minus NDHET. So N is the number of holes that we consider at a certain plane, at a certain section line. So we will be talking about this later on. So it depends on how many bolts are present in a certain column of bolt. Okay. DHE is the effective hole diameter. So this one, the nominal bolt plus 1/8 inch. And T is the thickness of the member. Because this one is the whole area, the area occupied by the hole. So the number of holes times the diameter times the thickness, right? So like this. So this one is the thickness of the member. This one is the effective diameter, right? So that's where this formula here come from. Okay. However, the determination of the net area is not just as simple as this one. So in calculating the net area, we also consider the so-called load transfer mechanism. So how do we consider the load transfer mechanism? So usually we consider it if, excuse me. All right, so let me go back. Okay, so load transfer mechanism is usually considered for symmetric arrangements, okay, of bolts. So for example, this one, if this is a plate for an example, so the centroid is at the center, right? And you arrange the bolts symmetrically, then you will be able to consider the load transfer mechanism. Okay. So how does the load transfer mechanism work? No? So we assume first that the force or the load carried by the member is equally distributed to each bolt. That's why the symmetry is important. That is in order for this assumption to hold true. If it is not symmetric, then we are not always sure that the load will be equally distributed. Okay. So now, how does this load transfer mechanism happen? So for example, we assume, so we have this connection detail right here. So this is the tension member. It is uh, it is subjected to a force P. So meaning there are three possible failure planes. Failure 1, failure 2, or failure 3. One of this may happen first. Okay. So if we consider section 1, if we draw the free body diagram up to this point, so what happens is that this plane right here, plane 1 right here, carries the entire load. Okay. So meaning, if you want to consider the capacity of this particular section, you will be considering the entire load for this one. Okay. Now, how about if it is, if we want to consider failure at section 2? So we draw a free diagram up to this point, but then, since this is symmetric, we can assume that each bolt will carry a load, no, equally, will carry a part of the load equally. So meaning, if we divide this by the number of bolts, each bolt will carry Pn over 6, right? So what happens then is if we cut this section, if we consider this section right here, what happens is it will not carry the whole load anymore. Why? Because the first two holes right here will carry uh, 2 Pn over 6, because Pn over 6 per hole, per bolt, right? So meaning it will only be carrying the remaining load, right? So this one will be carrying now 4 Pn over 6, which is just 2/3 of Pn. Okay? So do you get what I'm saying here? Do you understand so far? Okay. So and then if we consider the failure plane at section 3, again, we draw a free diagram up to this point, and then what happens is that it will not carry the entire load because some of the load will be resisted by the first two columns here. Okay, so for this particular area, it only carries 1/3 of the load. Okay, so that's how the load transfer mechanism works for bolted connections. So for calculating net area, we will be considering this. So how exactly do we consider this? We will be showing an example. Okay. So right. So now, uh, once you have so for example, we already calculated with load transfer mechanism in mind. So the net area here that you calculate is not yet the area that you will use for analysis or design. Okay. So we are only considering for now the first one, which is the presence of bolt holes. So we will be still considering another factor here, which is the shear lag mechanism. Okay. So once you have considered both, that's the time that you will be able to calculate the effective net area. So again, the effective net area is not always equal to the net area here, and vice versa. Okay. So now, how do we calculate the effective net area in this case? So to get the effective net area, you just have to multiply AN, the net area you calculated from here, okay? So you calculate it, then you multiply it by a certain coefficient U, which is called the reduction coefficient or the shear lag coefficient, okay? So this coefficient considers the phenomenon known as shear lag. So what happens during shear lag? So how do we describe shear lag? Shear lag is a phenomenon in which there is a lag or delay in transmitting tensile stresses from the connectors to the cross-section of the member itself. Okay? So let us show how shear lag happens. So for example, we have a tension member here, subjected to a load Pn, and then here's the connection right here. Then we consider that the critical rupture plane here goes at this point. So meaning it will most likely fail at this failure plane. Okay? And then what happens? So the so it may develop some rupture here, but the forces that act, the internal forces that act on this member will be distributed in this way. So meaning, if you apply the load here, no, the force will be felt most at this portion first before it will be felt. So the effects of the force will be felt first at this point. So mas ramdam dito kasi mas malapit siya do sa kung saan yung load rather than at this point. Right? So what happens is that, for example, if we consider the rupture plane here earlier, so yung effective area that is being that resists the load at this particular portion is actually ito lang. Why? Kasi because of the distribution of the force. Okay? Because of the effect of the forces here. So mas ramdam at this portion, so meaning mas we utilize the area more at this portion rather than at this portion. Okay? Due to the distribution of forces. So what happens is at this failure plane, the effective net area here, the only area that resists this this load will only be at this portion. Then this portion, hindi the effects of the load are not yet felt. So if we consider throughout the length of the connection, there is a lag in the development of the forces here. Okay, so that's what we call shear lag. Okay, that's why we also observe, for example, if we subject a material to tension, minsan nagkakaroon ng gantong klaseng failure pattern. It's because of this one. Okay, it's because of shear lag. Okay, so the shear lag here, the coefficient here aims to estimate the effective net area, the area that is actually carries the load at this particular plane. So it reduces the net area that we know, no, to an area that is actually effective in carrying the load. So this U right here is usually less than 1. Okay. So now, shear lag actually depends on two parameters right here. No? So before I proceed with that, no, so how do we actually calculate the shear lag coefficient? It is in NSCP, more specifically in table 504.3.1. So you may check this out. So I just included a screenshot of this particular page. No? So it depends on what type of member do you have, how are they connected. No? So that's it. No? So for commonly used tension members, so usually we use case 2. And we use the formula developed by Munse and Chison. So U is 1 minus X bar over L. So what is X bar? X bar is the distance between the centroid of the section and the plane of connection. Okay. So for example, let me this one is a bit unclear. So let me show this particular figure here. So please wait for a while. So if we consider this one right here, hindi lang masyadong, we cannot see it clearly na. So this is your connecting member right here, yung plate dito. And this one is another connecting member here, or vice versa. So for example, nandito yung connection mo. It is connected this way. So let me so for example, if the members are connected in this way, yan. So the plane of connection is actually this particular line right here, right? The interface between the plate and the and the uh, and the I-beam right here, this one. Okay, so so yan, itong part na to. So the distance from the member, so for example, ito yung tension member natin. So this part, so itong I-beam, ito yung tension member. Tapos ito yung plate natin, yung gasket plate natin. Okay. So we know that this is the plane of connection right here. Okay. Ito. And then nandito yung centroid ng I-beam ng tension member mo. Right? So the distance between that centroid to the plane of connection. So yung plane of connection mo is this one. Okay. So from the plane of connection, so the interface between the member and the gusset plate or the connecting plate. Okay. So the interface between them. And then, so the distance from that interface to the centroid of the tension member, that is yung X bar natin. Okay? So again, this one is the distance. So this one is the distance between the plane of connection and the centroid of the tension member. Okay. So we will have an example of this maybe later on or next time. Okay. So for now, please keep this in mind. Okay. So do you have any questions as to how we determine yung X bar so far? My questions? Wala. So sige. So for those who cannot actually get this one, no? So let me show a better illustration. We'll be going back with this no, later on. Okay? And the L is the length of connection measured parallel to the direction of the load. Okay? So center to center, length of connection. Okay? So this one is center to center. So I'll just show you an example later on how to apply this one. Okay? So for plates with bolted connections, since the X bar for plates is very very small, okay, we can actually consider U to be equal to 1. Okay? So there you go. Alright, so for some examples, so say we are given a tension member here with this particular detail. So so we assume that the connection itself and the gusset plate are adequate. So we are tasked to determine the critical effective net area of the given tension member. So consider the load transfer mechanism of the connections. So if we consider the formula alone, the more number of holes, the lesser the net area, right? So at first glance, you may actually consider already that the one at the 3 holes will be the more critical. Why? Because it has more holes, so meaning there will be less net area, right? However, we cannot actually just conclude that this would be the net area, the critical area. Why? Because we need to consider the load transfer mechanism. Okay, so first, so since this is although the drawing is not on scale, no, but and since this is a plate, so when we say PL 3/4 inch by 6 inch, no, so when we say this one, the thickness of the plate is 3/4 inch, and the width of the plate, so the dimension here is just 6 inch. Okay, so uh we consider this to be symmetric. Okay, so let's have this. So we assume that P is carried equally by the bolts. So meaning, for example, if we have P here, so since we have a symmetric bolt arrangement, we can assume that each bolt is carrying P over 5. Okay, and then two failure net sections will be considered for this example. So the failure pattern at B, so here, and the failure pattern at A. Okay. So we first consider section B, this one, the one with the two holes. So if we consider the free body diagram, if this is the load P, therefore this section right here will also carry load P. So 100% of the load will be resisted by this section. Okay, so there will be no adjustment in net area. Okay, so the net area, we just use the formula. So kung 100% of the load is assumed to be resisted, we just solve for the net area. Okay, by itself. So there's no need for adjustment yet. So it's just AG. The gross area of the plate is just 34 times 6. Okay. Minus the number of holes, 2. Then the effective diameter, which is equal to the bolt diameter. Bolt diameter is 3/4 inch. Then you add 1/8 to it. That's why it becomes this way. Okay. And then the thickness, which is 3/4. The thickness of the plate. So the net area is just 3.1875 square inch. So the net area at this portion. And then for plates, we use the reduction coefficient equal to 1. So the effective net area is just pretty much the same as the net area, which is equal also to 3.1875 square inch. Okay. But this is not yet the answer because we still need to consider the other section here, which is section A. Okay. So for example, so now we consider section A. So we cut a section through A and then we draw the free body diagram. In this particular case, this is the tension load P. The other two bolts are already resisting their portion, 2P over 5. So meaning the uh, the remaining load, no, will be carried by the section, which is now be equal to 3P over 5 by static equilibrium. Okay? So, from here, we can only say that if section A is to be considered, only 60% of the load is to be carried by the said section. Since the remaining 40%, the remaining 2 over 5 will be carried by the first two bolts in section B. Okay? So what will we do first? So first, we solve for the net area of this section. So pretty much the same formula. The gross area, this one, and then this time, since there are 3 holes, you use 3 here. So it becomes this way. However, this is not yet the net area to be considered here. So if we have 60% of the load to be carried on, only to be carried, what happens is that we adjust the net area to take account the expected load distribution. Okay, so what happens is that the net area that you calculate from the formula, you just divide it by 60% or 0.6 because it only carries 60% of the load. So we will now adjust the net area such that we now consider it to be 100%. So it's just pretty much a play on ratio and proportion. So if more load is to be carried, therefore there should be more area. No? So it becomes that way. So in this particular case, the adjusted net area is just the net area that you determine from the formula here, divide this by the percent of the load. So in this case, since this is 100% earlier in section B, there's no need to do that adjustment. Because if you divide this by 100%, it's just pretty much dividing it by 1. No? So in this particular case, we divide this by 60% or 0.6. So what happens is this will be larger than what is determined here. So in this case, so the adjusted net area in this case will just be equal to 4.21875 square inch. Okay, so the net area that you use for the effective net area in section A would be this one instead of this one. Okay, So for plates, again, the reduction coefficient is 1, so you take the effective net area. Okay? And then, considering the load transfer mechanism, so now, which one should we choose? The one in section A or the one in section B? So when we say critical section, we choose the one with the lesser area. Okay? So in this case, the critical net section would be at section B, since it gives less effective net area. So therefore, the critical effective net area of the member is the one that we solved from section B, which is equal to 3.1875 square inch. Okay. So there you go with our first example. So do you have any questions? Alright, so I guess the example is pretty clear. Okay. So pretty straightforward lang naman to. Alright. So now, what if in some cases, uh, so in some cases, the bolt arrangements may not always be symmetric. Okay. So how do we go around with that? So let's go with the next section. So due to construction